Hello, welcome to the DataFest 2020 Uncertainty in Machine Learning track. My name is Andrey Malinin, and today I will tell you about how to evaluate the quality of uncertainty estimates. So in the previous videos, we discussed what are the sources of uncertainty. We have data uncertainty, which is caused by class overlap for classification and additive noise for regression. And then we have knowledge uncertainty, which is a result of dataset shift, anomalies, and in general situations where test data comes from regions which are either not covered by training data or sparsely covered by training data. We learned that we can use ensembles of models to estimate both uncertainties. Data uncertainty can be estimated as the average entropy of the ensemble or the average variance of an ensemble of regression models. Knowledge uncertainty can be estimated via measures of ensemble diversity. Now, in this video, we asked the question of how to evaluate the quality of uncertainty estimates once we've obtained them. Now, one of the standard ways of assessing uncertainty is via test set negative log likelihood. Essentially, it is the average negative log likelihood of members of a test set. It essentially asks the question of how calibrated the model's probabilities are. How well do the model's probabilities correspond to empirical probabilities of events? If negative log likelihood is lower, it means that the model thinks that the test dataset is more likely, and therefore its assessment of uncertainties is better. Now, this is an informative quality metric, but it is a task agnostic metric, and therefore it is weakly related to applications of uncertainty estimates. In general, uncertainty should be assessed in the context of a particular application. For example, threshold-based outlier detection, such as error detection or misclassification detection, out-of-distribution input detection, and adversarial attack detection, or active learning or reinforcement learning uncertainty-driven exploration. In each of these cases, uncertainties can be used in different ways, and the quality of uncertainty estimates should be assessed within the context of these applications. In this video series, we'll cover threshold-based outlier detection and active learning. However, active learning will be presented by Yegor Kolodin in one of the later videos, and in this video I'll focus on threshold-based outlier detection. The basic idea of threshold-based outlier detection is that you have two datasets. You have your test in-domain test dataset, or a clean dataset, and then you have a dataset of anomalies or outliers or errors. Now, using a detection rule, as defined here, if the uncertainty measure, which is h of x is any uncertainty measure. It's the entropy or the diversity or the variance, doesn't matter. Let's assume any uncertainty measure. If the uncertainty measure is bigger than the threshold, then we consider this particular sample to be an outlier. It's an error or an anomaly or an out-of-domain input or something like that. If the uncertainty is lower than the threshold, then it's a good normal example. Now, the performance of this task, so the idea of this task is to basically be able to discriminate between in-domain data and out-of-domain data, or clean data and errors. Now, we evaluate performance on these tasks using area under an ROC curve. This is used for out-of-distribution detection, where we have balanced data sets, equal amounts of in-domain and out-of-domain. And error detection is typically assessed via the area under a precision recall curve. Now, an ROC curve is defined as the true positive rate versus the false positive rate at a particular threshold. So we draw the curve by varying the threshold, and we draw the points which correspond to different true positive and false positive rates. The true positive rate is the number of true outliers we have detected at a given threshold, out of the total number of outliers. And the false positive rate is the number of in-domain examples or correct examples which we have classified as incorrect or out of domain at a given threshold. Now, the area under an ROC curve is 100% if you have an ideal detection scenario, and 50% if it's completely random. It will be less than 50% if we have a perverse situation where we think that the in-domain dataset is more uncertain and the out-of-domain dataset is less uncertain. Now, for the precision recall curve, we plot the precision, which is the number of correct positive examples or outliers we have detected out of all the outliers we have detected. And the recall is the number of positive outliers we have detected. Now, this is particularly good for misbalanced data sets. So if you have a data set, for example, in error detection, where you have most of your data set is clean examples, like, for example, if your error rate is 5%, then 95% of your data, of your test set, is good and 5% is errors. Now, clearly this is misbalanced, and this is the correct way to assess this is via the area under precision recall curve. Now, good performance is again 100%, but random performance isn't 50 like for the ROC curve. It is the base error rate of your classifier. So if your error rate is 5%, then the random performance corresponds to a 5% area under a precision recall curve. Now, this means that you cannot truly compare precision recalls or area under the precision recall curve across models with different error rates or models which make different errors. But you can compare across the same model but different measures of uncertainty or different ways of estimating uncertainty for a given model. Now, here I have drawn the ROC curve on the left and the precision recall curve on the right. So if you would imagine a diagonal line between 0.0 to 1.1 here, this diagonal line on the left would correspond to the random performance. And here we have models which actually perform quite well. On the right, we have the precision recall curve, and here random performance would correspond to a horizontal line at the level of the error of the model. Now, one way in which we can compare models of different base error rates, and something which actually is a little closer to a real application, is something called the prediction rejection curve. So this assumes we have a hybrid scenario. We have a model which is making predictions, but we also have access to a human who we can query for the correct answer. But we'd like to query the human as less or as little as possible. So for example, so here on the x-axis, we have the percentage of examples we reject to the human, to the oracle. At 0, we are, the model is doing everything and has the base model error rate. And at 100, the human is doing everything, and we assume in this scenario that the human can get it all correctly. This isn't always true, but here, assume that the human is an oracle and knows the correct answer. So here we have a scenario where if we were to reject examples in the order of error, so if we just first reject all the ones where we make mistakes, then we can drop our error rate very sharply. If our error rate is 7%, then we need to reject just 7% of the data set to the human to get 0% error, because the machine can handle the other 93% of the data set. Now, obviously, this assumes that we know which examples are actually incorrect. Now, if we randomly reject examples to the human, then in expectation we'll have this straight line here, the straight black line. This represents random or the worst performance we can have. Now, in practice, if we reject examples to the human in order of decreasing uncertainty, so first we estimate uncertainty for every example in the data set, and we reject the ones which have the biggest uncertainty, then the next biggest uncertainty, and so on. We'll get this orange line. Now, this orange line will lie somewhere between the black line and the blue line. And the closer it is to the blue line, the better it is. So this orange line represents the actual performance you get in uncertainty-based rejection. So this shows that it represents your performance trade-offs. You can reject about 10% of your data to the human and go down from an error rate of about 7 point something to 4. So you've cut your error rate drastically, and you're still handling about 90% of the data set, but the humans do 10% of it. And maybe that's fine in certain applications. Maybe you can do better in certain applications, or maybe that's too expensive. It depends on the application. But in general, this line represents the possible trade-offs. Now, one way you can compare, so you can't compare these lines across different models because they start at different places, but you can compare the ratio of the areas across models. So if you consider this yellow area here on the right, if you consider the ratio of this area to the area between the blue curve and the black line, then this ratio will be 1 if the uncertainty, the yellow curve, the uncertainty rejection yellow curve matches the oracle curve. and if it is completely random, the ratio will be 0. So this is called the prediction rejection ratio. Like AR UNS is the area between the yellow line and the black line, and AR ORC is the area between the oracle blue line and the black line. This is a summary statistic which allows you to compare the performance in these prediction rejection tasks across models with different base classification performance. So this brings us to the end of this talk. We've learned that one way of assessing the quality of uncertainty is via calibration and negative low likelihood. Another way is via these area under the ROC and precision recall curves for threshold-based outlier detection. And you can also use these prediction rejection ratios and rejection curves for assessing the quality of error detection. So hope you've liked these videos. In the next video, Arseniy Ashuha will then tell you about how to make different ensembles and compare different approaches to making ensembles. And I will then give one last lecture at the end of the track. Thank you very much. Hope you liked it.